warm up while everybody's entering the classroom. Find radius of convergence. And the interval of convergence. Of our series x to the 2k plus 1. Nope, let's go x to the 2k minus 1 over 2k minus 1. And the radius of convergence and the interval of convergence. X to the 2k minus 1 divided by x to the 2k. Remember how you can start? By the ratio test. Find where the ratio test in absolute value is less than 1. That's what you're solving for x. Guilt you into coming in? Make yourself at home. This is our new home. Find the radius of convergence and the interval of convergence. Solving where the k plus first term divided by the kth term in absolute value has a limit smaller than 1. What you're solving right there for this particular expression. Solving that for x. Remember to check the endpoints. Kind of a quickie. Just in case you're going slow. I mean, we're already a half a minute into class. You should be done by now. To get your radius of convergence to just be 1. And then at each endpoint, I think it's going to converge. So your interval of convergence, I think, is the closed interval from -1 to 1. Am I right? Anybody check the endpoints yet? -1 in there, -1 to the 2k minus 1, 2k minus 1. That makes it an open series, right? Then it goes 0 to another. So I think it only converges at one of the endpoints. At the -1.
ratio.
Let me catch up with you. Let me do the ratio test. Okay, so the k plus first term is going to look like x. I'm putting a k plus 1 in right here. Then I subtract the 1. Same thing down here. 1. There's the k plus first term. Then I divide it by x to the k, so I flip and multiply. That's smaller than 1. So this becomes 2k plus 2 minus 1. So that's 2k plus 1 on the x. And that's going to be a 2k plus 1. That's a 2k minus 1. And that's an x to the 2k minus 1. Right? So really nothing cancels but the x to the 2k's. X to the first divided by x to the negative 1. What is that?
X squared.
That's x squared. So I'm going to put that out front. So I have x squared here, and then I've got the limit of 2k minus 1 over 2k plus 1. And that's an absolute value. We don't need it, but I got it there. And we need to find a solution to that equation. And so I got this limit, where the power on top is the same as the power on the bottom, so I get the ratio of the coefficients. So that limit's just 1. So we're solving x squared in absolute value is smaller than 1. So that says x squared is between 1 and negative 1. X squared can't be between negative 1. How do I want to say that? Okay, let's just go to here. Let's say this. Now think about what I'm describing. I've got a parabola smaller than 1. So that should occur between the two x-intercepts. So that itself says x is between 1 and negative 1. So my radius of convergence is equal to 1. Now we're going to check the endpoints. At x is equal to negative 1. Going back to the original series, and I'm going to plug that in. And so I'm going to have negative 1 raised to the 2k minus 1 over 2k minus 1. And I have that series. So this 2k minus 1 alternates between positive and between even and odd numbers. When k is 1, it's odd. When k is 2, oh, it's always odd. It's always odd, right? Okay. 2k minus 1 is always odd, so that's always a negative 1. It's not alternating. It's always negative 1. So I'm going to pull a negative outside. Right? This is always odd. So I always get negative 1 to an odd power, so that's always negative 1. So I'm looking at testing this series. What do you know about that one?
You compare it to a P series.
You can compare it to a P series. There's a P series that you compare it to, converge or diverge. It's a divergent, compares to a divergent P series. We can do an integral test. Integrate that and get a logarithm, so it diverges. Right? This has less on the bottom, so it's bigger than divergent is divergent. That's your comparison test. Okay, and then the other one just has a 1 in there. At x is equal to 1. We just have 1 over 2k minus 1 without the minus sign out front. So it is the same divergent thing. So it's an open interval from negative 1 to 1. So our interval of convergence is open. And our radius of convergence is just that 1. Okay. I want you to remember that function because we're going to find out what that converges to on this interval. That's exciting. Do you remember that we can take derivatives term by term and antiderivatives term by term? So on the interval from -1, the derivative of this thing will be x to the 2k minus 2, because the x to the 2k minus 1s would cancel. Yes, in summation. And the antiderivative, add 1, divide by the new power. Okay, good. So remember that, put a circle around it, and we'll come back to it before we leave class today. If we don't, I'll just lock the door and we'll come back to it before I let you leave class today. Because I said there was this thing called the Taylor series. The Taylor series was a series representation of a function on an interval, where that function on that interval had an infinite number of derivatives. And I showed you a formula of how to get that function, but now I'm going to show you where the formula comes from. So we're back to section 8. We'll talk about Taylor series and Maclaurin series. So the claim is that if f is a continuous function with an infinite number of derivatives that are continuous, then we can write f as a polynomial. Let's see, continuous derivatives in an interval containing some number c. And we can write f as a polynomial. So f of x can be written as a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed plus a4 times x minus c to the 4th, and so on. That's the big idea. Find that polynomial that represents f in an interval containing c. You want it to match all of the characteristics of f in that interval. So you want it to pass through the same point. So in other words, we want f of c here to take on the same value as f of c there. So we want, so this tells you right away what f of c is going to equal to. You put a c here, and here, and here, and here, and all of the terms out here, those terms disappear. So f of c is a0. Now let's take a derivative of this polynomial. F prime of x, all right, that's a constant, so its derivative is 0. When I take the derivative here, the derivative inside here is just 1, so I get a1. The derivative here gives me 2a2 times x minus c. The derivative here gives me 3a3 times x minus c squared. The derivative here gives me 4 times a4 times x minus c cubed. And then I have all those derivatives out there. So in building this function, I also want the first derivative at x is equal c to be the same. So if I plug c in for each x, I have that f prime of c is a1. So here I know that this is f of c, and here I know this is f prime of c. Now I want my second derivatives at that point to agree. I want them to have the same concavity at that point. So let's take the second derivative, plug in c for x, and see what that variable that gives me. So the second derivative of that is 0. The derivative of that is 1, so I get just 2a2. The derivative here gives me 6a3 times x minus c. The derivative here gives me 12a4 times x minus c squared. Plus all those other terms. So when I plug c in for x, it tells me that 2a2 is f double prime of c. So if I solve that for a2, then I get a2 is f double prime of c divided by 2. Hang on to that. Hang on to that one. I'm going to hang on to that one. So I'm solving for my coefficients. I'm going to do a third derivative. So let's take a third derivative from here. Put it up here. So my third derivative says, all right, I'm taking the derivative, so that's a constant. Its derivative is 0. The derivative of this x is 1, so it leaves me a 6a3. The derivative here gives me 24a4 times x minus c. Plus all those other terms. But I want this derivative, that's x. But I want this derivative when x is c to agree. So when I put c in for all the x's that are going here, so it says the third derivative evaluated at c is 6 times a3. So f double prime at c divided by 6 is a3. Without taking a fourth derivative, can you tell me what the fourth derivative at c is going to give you?
Base of 4 over 24.
That's right. So if I put the 24 here, I get a4. So what I want you to recognize is that 6 is the same as 3 factorial. And that 24, take a wild guess, is 4 factorial. 2 is the same as 2 factorial. And then, of course, 1 is the same as 1 factorial. And 0 factorial is also a 1. So that's where Taylor's formula came from. It said if I want to write f as a polynomial, I replace these with what I just found them to be. So I'm going to go back there and erase them and fill them in. This one was f of c. This one was f prime of c divided by 1 factorial. A2 was f double prime of c divided by 2 factorial. A3 was f triple prime of c divided by 3 factorial. And A4 was the fourth derivative of f at c divided by 4 factorial. So in general, the Taylor series for f of x centered at x is equal to c is given by that thing that I've just written. But I'm going to write in summation form now. I said we've got an order on the derivative, so let's call that k. At point C divided by k factorial. That's what the coefficient will look like. and then the x minus c to the k power, and I'm starting k at 0 and going to infinity. So if k is 0, I'm denoting the 0 order derivative as just being f of c. And again, 0 factorial is just 1. Yes?
Can I ask an off-topic question?
Sure.
So notice, I know the kind of like one factorial is one, and zero factorial is one, how the rest of the one is just one factorial is one.
Right?
What's negative one factorial?
There's no such thing. Factorial is defined only for integers, 0 and greater. So there's no such thing as a 1.5 factorial. Non-negative integers only.
How is zero factorial?
It's a counting manipulation to make the definitions hold from all out. You can think of a factorial as the number of ways to put k items in a row. So if I called 3 of you up here and put you in a row, I can have 3 factorial manipulations of it, right? A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Those are the 3 different standing orders. So 3 factorials, number of ways to put 3 things in a row. 2 factorials, a number of ways to screw up 2 things. 1 factorial is a number of ways to put 1 thing in a row. You stay here. 0 factorial is a number of ways to put 0 things in a row. There's only 1 way to do it. Just stand here and don't do anything. Okay, so there's 1 way to put 0 items in a row. Okay, so there's the formula for a Taylor series, and remember how to get a Maclaurin series?
We'll get C for 0.
Take C to be 0. So when C is equal to 0, we have a Maclaurin series. And so the Maclaurin series just looks like this. Kth order derivative of f at 0 divided by k factorial times x to the k. So if a function is well defined at 0 and in an interval containing 0, we typically use a Maclaurin series. We use a Taylor series when we have our graph shifted over for some reason or another. Like for instance, the natural log of x is not defined at 0, but it is defined for numbers bigger than 0. In fact, let's start there. Let's take the natural log of x and let's write a Taylor series for the natural log of x centered at x is equal to 1. Now it's only one Taylor series that makes it true, right? If the function has a Taylor series, there's one and only one, because these numbers are unique for that function. So write the Taylor series for f of x is equal to the natural log of x centered at x is equal to 1. So I'm going to call it C. C is equal to 1. So to start it, what we're going to need are a bunch of derivatives. So let's just see how many fit on the board here. Oops, I'm going to move that over. There you guys can see, huh? I think that's what the chat says. I can't see a damn thing. Yep. I got to try to remember to move my camera, so just be patient with me. Now you can see it. There's the formula for the Taylor series. Take C to be 0, you got the Maclaurin series. So when we're building our own Taylor series, we don't jump right to the formula in summation form. We think of the formula, what it looks like all spread out. And what we need are those coefficients of the x minus 1s to a power in this example. And so we generate them by brute force. Just start taking derivatives. So f of x is the natural log of x. F prime of x is 1 over x. F double prime of x is negative 1 over x squared. Now you take over. The simplified version of f triple prime. Positive 2 over x cubed. Now the fourth derivative, I'll just start putting numbers in parentheses. Okay. The fifth order derivative. How much?
On the fourth one, it's x,
Oops.
24 x.
Positive 24 over x to the fifth. I got room for one more. The sixth order derivative.
144 x over x.
How about 140? Yeah, how about
120.
120? 120. 4 times 5 is 20. So 120 negative over x to the sixth. Now we have to evaluate all of those at the given number c, and we chose c as 1 to make this evaluation quick and painless. So f of 1 is the natural log of 1, 0. Now I'm putting 1 in for each x here. 1 over 1 is 1. F double prime at 1 is a negative 1. F triple prime at 1 is a 2. The fourth derivative at 1 is negative 6. The fifth derivative at 1 is positive 24. And the sixth derivative at 1 is negative 120. Okay, so now I'm going to write it out in its long form, not in its summation form. I'm going to write it out in long form.
We always tell us how many derivatives to take, or do we just? take
And
it?
the tricky part is to see the pattern. So maybe how many derivatives it takes for you to see a pattern. If I know the pattern's not going to be obvious, I'll say, the way your web work says it, it calls these Taylor polynomials of different orders. So T1 just has the constant term. T2 is the constant term plus, no, I said it wrong. T0 is the constant term. T1 takes you to the x minus c to the first power. T2 takes you to x minus c squared. So I'll say write a fourth ordered Taylor polynomial. So you take me all the way to x minus c to the fourth. You'll see with sines and cosines, a lot of the terms are zeros. So I'll say, give me the first 4 non-zero terms of the Taylor polynomial. But this one, I kind of hope that you're already recognizing my pattern of numbers. You can already see they're alternating. But look at the magic in the numbers. 1, 2, 6, 24, 120. Those are factorials again. Okay? All right, so we're going to write this out. That I'm going to erase it here, right here. Okay, so here's the general formula written out. There's nothing to memorize. It's kind of easy. It's got that obvious pattern to it. So I'm going to fill in hours. Our function is the natural log of x. So here I'm going to have the natural log of x. My c is 1, so f of 1 was 0. F prime of 1 was 1 over 1 factorial times x minus 1. F double prime of c was negative 1, so I'm going to put a minus here. The next one's going to be a positive 2. Okay, so I did, that one is f of c, that one is f prime, f double prime, f triple prime. So we're here with a -6. So it's going to have an x minus c to the 4th over 4 factorial. Then we're going to have plus 24 times x minus c to the 5th, and this will be over 5 factorial. C is 1, sorry, x minus 1, no x minus c is x minus 1. Okay, so that takes care of the 24, minus 120, x minus 1 to the 6 over 6 factorial, blah, 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 blah. But this simplifies. I said, remember what these numbers were. This one here is going to be 1 factorial. This is 2 factorial. This is 3 factorial, 4 factorial, 5 factorial. So for instance, how can I reduce the fraction 5 factorial divided by 6 factorial?
6 times 5 factorial.
Just plain old 1 over 6, right? Because the 5 factorial cancels with the 5, 4, 3, 2, 1 that is embedded in the 6 factorial. So I'm going to simplify all of those coefficients, and I'm not going to write the 0 anymore. So I'm going to write this as x minus 1 minus 1 over 2 factorial, x minus 1 squared. I'll go ahead and put the 1 factorial here. And then I don't want the factorial because I'm going to cancel the factorials. So then I'm going to write this as 1/3 times x minus 1 cubed minus 1/4 times x minus 1 to the 4. This 4 factorial cancels here, give me plus 1/5 x minus 1 to the 5th. That's a 5 factorial, so I get minus 1/6 x minus 1 to the 6th, and so on. Now my challenge to you is to write this in summation form using the variable k. Yes, sir.
So I know there's some pattern, but this might be the wrong side of understanding. Like for example, 24 over 5 factorial is efficiently 4 factorial over 5 factorial.
Correct.
And that simplifies to 5.
Right.
5. If we had something like, let's say, 3 factorial over 5 factorial, that would simplify to 2 factorial.
No, that simplifies to 5 times 4. Right, because 5 factorial is 5 times 4 times 3 times 2 times 1. So 3 factorial is the 3, 2, 1.
There's the quick and easy way to factorial divided by factorial.
No, unless they're right next to each other. Right, if they're next to each other, and then we cancel the factorial and stick the bigger number there. Okay, so my challenge was for you to write this as a formula. Here's the summation symbol. Now let's take care of the alternating part. Let's put a minus 1 to the something here. Depends on whether you want to start k at 0 or k at 1. My first x minus 1 has a k as 1. So let's start with k is equal to 1. So I need my first sign to be positive. So what should the power on here be? K plus 1. Okay, now you're in charge of the next bit. What happens after the alternating sign? You're going to have x minus 1 to the k divided by k. I don't want that there. Agree? Does that look like all the terms? Does that generate an alternating series? K is 1, I get a negative 1 squared, so that's a positive 1, x minus 1 to the first divided by 1. So that gives me that one. K is 2, I have x minus 1 cubed, so it is negative. K will be 2, x minus 1 to the second. So the reason I wrote it like that is because I now want you to tell me what the interval of convergence is. Do the ratio test and find the interval of convergence. You're going to put it in absolute value bars, so you can go ahead and blow off the -1 to the k plus 1. So I'm just going to go with the x minus 1 to the k plus 1 divided by k plus 1 times k, x minus 1 to the k. We want to find where that has a limit smaller than 1. Sorry? Yeah, it's going to cancel to a -1 to the 1, and that's about -1 is. So the only thing that really cancels is the x minus 1 to the k. Right? We're going to take out the remaining x minus 1 in its own absolute value bars and take the limit with what's left. Okay, so that's just going to be a 1. So that says x minus 1 is smaller than 1. So what this tells me is this: the radius of convergence is 1. The center of my interval is this one. So here's my center of my interval. If I go 1 unit out there to 2, or 1 unit back here to 0, then the interval of my convergence is between 0 and 2. But now we got to figure out, do I want parentheses or brackets or some sort of mix? Okay, so let's test the endpoints. So let's let x equal 0. So we're going to go over here and let x equal 0 and test the remaining series. And so I have the sum of -1 to the k plus 1. Put a 0 in there, that becomes -1 to the k all over k. All right, so I'm just putting a 0 right here in for x. Because when you multiply like bases, you add exponents. So that gives me a power of 2k plus 1 on the -1. Let's do it over. And no matter what k is, when I double it, it becomes even. And when I add 1, it becomes odd. So this is an odd power for every value of k, which means this is always a -1 times 1 over k. So I can pull it out. What do you know about the series 1 over k? It diverges. So it's an open endpoint here. Well, doesn't that make sense? The natural log of 0 is not defined. So that endpoint shouldn't be in there at all. Now, the natural log of 2 is defined, but whether that point is in the interval of convergence with its power series is yet to be seen. So now let's put x is equal to 2 in here and see if it does include that endpoint. So here's the -1 to the k plus 1. Then I have 2 minus 1 to the k. So 1 to the k, right? Put a 2 in here. 2 minus 1 is 1 to the k. 1 to the k is always 1, no matter what k is, right? So I've just got a 1 here, and then k factorial. Not factorial, just k. What do you know about that series?
Alternating P series.
It's an alternating P series, and every alternating P series in the world converges. So this converges. So that endpoint is included. So this is the power series for the natural log of x, and the interval of convergence is from 0 to 2. So if I were to graph you the natural log of x, it looks something like this. Here's x is 1, here's x is 0, and let's say here's x is 2. That power series is doing this. And the rest of it might do something else, right? It doesn't match the graph there. But over this interval, from 0 to 2, it's smack dab on top, and everything else might do something else. Okay? Okay. If I want to find now, for instance, an approximate value for the natural log of 1.5, I can just stick 1.5 in for x. The natural log of 1.5, I put a 1.5 in here, and then I stop adding terms whenever I'm at a level of accuracy I want. If I want to keep it within 0.01, whichever one of these doesn't affect the second decimal place, I throw away. Okay? But if I want to approximate the natural log of 4, I can't, because this only converges on the interval from 0 to 2. If I want to approximate the natural log of 4, then I need to make a shift and move this over so that it's centered where 4 would be included in the interval of convergence. Like, let's see, if I want this number to be a 4, then this would be the 2, and then I would center it at x is equal to, how do I make that? X is, I want that, this one has a center of 1. So if I want to center it, say, at 4, or even have a 4 in here, then this would be a 5, and that would be a 3. So this was at x minus 1. And so if I want to go, I just, I want to move to 4, then I need to replace each x minus 1 with an x minus 5. And then I can use that to approximate my power series. Okay, all right. There are several known power series that are Maclaurin series for you to memorize. This is a Taylor series because it is centered at x is equal to 1. That's easy to remember, it's easy to do. But the Taylor series for sine and cosine are pretty interesting. Let's find the Maclaurin series centered at 0. So I want you to do the same thing, but let's use f of x is equal to sine of x and centered at c is equal to 0. So take me about 6 or 7 derivatives of the sine of x, evaluate each of them at 0, and then let's write that Taylor series. I don't call them all Taylor series. I still am pissed off at Maclaurin for taking the name for x is 0. And we shouldn't feel so badly about that because Maclaurin discovered something called Kramer's rule, but Kramer stuck his name on it. So that's just a little bit of sweet revenge from Maclaurin to take something from Taylor. Okay, so you're going to let f of x be the sine of x, and you're going to find the Maclaurin series for this particular function. So that means c is equal to 0. Did we? You may have. You got a bunch of even terms?
Yeah.
And then you took derivatives and got the odd terms?
Yeah.
Oh, backwards. Sine is odd, cosine's even. So let's see if you remember it. Sine of 0 is 0, right? Derivative of sine is cosine. Cosine of 0 is 1 times x over 1 factorial, right? Derivative of cosine is a minus sine, but sine of 0 is 0. Derivative of minus sine is a minus cosine, so my next term is going to be a negative. What power is going to be on it? And then the next one will be plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. That's right, I'm glad we did that. So instead of taking all the derivatives, if you remember the Maclaurin series for the sine of x, then how did we find the Maclaurin series for the cosine of x? We took the derivative. So the cosine of x is going to be 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus 9x to the 8th over 9 factorial. But remember how the 5 and the 5 factorial cancels? Leaves me with 4 factorial, right? Each one knocks it down by 1 factorial. So the cosine of x looks like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. Did we do the Maclaurin series for e to the x? Well, let's do it in our head. What's every single derivative of e to the x?
Yes.
Evaluate every single derivative of e to the x at 0.
One.
And now let's fill it into the formula. Every coefficient is going to be a 1, right? Divided by whatever factorial that the power is. So the Maclaurin series for e to the x, f of 0 is 1. F prime of 0 is 1, so 1 over 1 factorial times x. F double prime of 0 is 1 over 2 factorial x squared. F triple prime of 0 is 1 over 3 factorial times x cubed. Can you write that for me in summation form? X to the power of k over k factorial, where k goes from 0 to infinity. Can be shown that the interval of convergence, we may have done this, is from minus infinity to infinity. So tell me, what does this power series or this series converge to? This is a convergent series. You can use the ratio test to show that it's convergent over some interval, the whole number line. It converges, but what does it converge to? E to the 5th. E to the 5th. So if it's a known power series, now we can tell what power series or the series itself converges to. All right, I just replaced x with a 5. Okay. All right, what does a geometric series look like when I write it all spread out? Anyway, say its first term is a and its multiplier is r. What's it look like? A plus AR plus AR squared plus AR cubed, AR to the 4th. So it looks something like A times R to the K. K is equal to 0 to infinity, maybe. For what values of R will that converge? Converges for what does it converge to?
A over 1 minus I.
So now let me ask you to write the power series representation of 1 over 1 minus x. What power series corresponds to 1 over 1 minus x? And there's your hint. That is that. I replaced A with 1. I replaced R with X.
X to the
So let's write it out like this. Each A is 1, each R is X. So it looks like 1 plus X squared plus X cubed plus X to the 4th, and so on. Or I can write it in summation notation. It's the summation from K is equal to 1 to infinity of X to the K. Let's go K to 0, so I can start with 1. Okay. What do you think the power series representation for this is? If that's the power series representation for 1 over 1 minus x, what substitution can I make to get the power series for this? Think of it as A over 1 minus R. A is 1. What is R?
negative.
Negative x squared. If I take that line and replace each x by negative x squared, boom, I got the power series for that. So each x is negative x squared. So let me simplify that. It's 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th. Or in summation notation, it's the sum from k is equal to 0 to infinity of minus 1 to the k, x to the 2k. Agree? I can make a term-by-term substitution on its interval of convergence. So this is valid for every r smaller than 1. This is valid for every x between 1 and negative 1. So that's the same thing here. What do you get when you integrate this thing? Don't tell me that yet. What is the integral of 1 over 1 plus x squared? So now I want you to integrate term by term to tell me the arctangent power series representation. It's the integral of each of these terms. So if I integrate that, I get x. If I integrate this, I get minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, plus x to the 9th over 9. I integrate it in its closed form. It's a minus 1 to the k, x to the 2k plus 1 divided by 2k plus 1. That's the power series we started with today. And you found its interval of convergence to be what? This same open interval, right? And that's why. It comes from a geometric series. A substitution, then a term-by-term integration. So some power series we're going to generate by taking a bunch of derivatives and filling them in the basic formula. Some we're going to find by taking derivatives of known power series. So the ones you should know are e to the x, the geometric series, sine and cosine, and now we've got the arctangent. You don't have to memorize it because you can just integrate that one. Okay. I just think that's just awesome, huh? And so this is valid for every value of x between -1 and 1. And so if I wanted to know what the arctangent of 0.2 was, I just put 0.2 in for each x and get out my calculator and do powers of 0.2. Okay? Because my calculator doesn't have arctangent. Okay, so with that warning, some of the problems on your web work, you generate the Taylor or Maclaurin series by taking derivatives. Some of them you don't. Like for instance, if I want to generate the Taylor series for the square root of x times the sine of 4x, I'm not going to start taking n derivatives of this using the product rule. I'm going to take the Taylor series for the sine of x, and I'm going to replace each x with 4x. Then I'm going to do a term-by-term multiplication by the square root of x. And that's the Taylor series for x, a square root of x sine of 4x. Okay? So use your wits when you do this web work. Don't just dive in and start taking a bunch of derivatives. If the derivative's real messy, then you're doing it wrong. Okay? All right, I think we're done, okay? Had to really talk fast to get back to that first example. You gonna help you?
Oh, no, I appreciate you.
Yeah, wait till you wipe out and smack your face.
Oh, yeah.
All right, that's fine.
All right, bye-bye. Okay, everybody's done, blah, blah.